Okay, so today hopefully is going to be shorter than the previous ones, not because there isn't much to say, there is lots to say, but there isn't much to say that I know very well. The goal for today is to simplify Surf graphics by reducing to only critical points of two consecutive indices. And last time we basically discussed how, given a Surf graphic, we can rearrange it and show that any Surf path between functions with no critical points is homotopic to an ordered Surf path. Well, by ordered, I mean that all the functions have critical points, so that if you have C1 and C2 Morse critical points with f of C1 greater than or equal to f of C2, then I must have then the index of C1 is greater than or equal to the index of C2. That's the condition of being ordered. But we haven't done anything really yet, like we haven't actually canceled any critical points. We haven't simplified drastically the Surf graphics. We've just rearranged the order in which the various critical points within the Surf graphic shows up. Today we will show how to cancel critical points. And the input is going to be an ordered Surf graphic, sorry, an ordered Surf path. And unlike last time, we will make extensive use of the swallowtail, which we mentioned last time, but we didn't really use. And also a special kind, so that's a typo, a special kind of Surf path, of ordered Surf path, which we call SMAIL path, which I'm going to show up. It's going to show up in a second. And let me just say that we are following chapter V.2, 5.2 of Surf very closely. So at some points, I'll have pictures from actually like Surf's book, and we can go through them. But that's roughly the plan for today. Is that okay? So the first kind of thing that we have to introduce those spaces, which I'm calling here f sub I. So the actual reduction is quite nice and quite visual, but until we get to that point, we have to introduce some new spaces to we can work with. And for the entirety of this talk, V is going to be some n-1 dimensional manifold. Very soon, I'm going to assume that V is simply connected, but not just yet. And W is V cross I. So that's going to be for the entirety of the talk. If you remember, I had introduced this notation where curly F of W is the space of all smooth real valued functions on some manifold W. So now for this talk, I will just be denoting that as curly F, and whenever I just have a curly F, you should assume that the input here is W. And usually there's going to be curly F with some kind of decorations, either as an index or as a sub-index. And by that, I will mean some kind of subspace of f of W, the space of C infinity real valued functions. And I'm going to try and specify what that subspace is. If not, you should ask me. So that's just the setup for the talk today. And the first definition that I want to give is basically if you choose any I between 0 and n-1, and you also choose any non-negative integer q, I'm going to denote by f sub I comma q this subspace of curly f, which is formed by all ordered Morse functions with exactly q critical points of index I and exactly q critical points of index I plus 1 and nothing else. That's what f sub I comma q is. Right? Ordered Morse functions, exactly q critical points of index I and I plus 1. And I am also denoting by f sub I comma q semicolon alpha the subspace of f1 alpha. So f1 alpha was this stratum that contained the cusp critical points. And I just want to look at a subspace of that which separates fi comma q from fi comma q plus 1. So if you want to look what this looks like in terms of what I'm calling here Morse graphics, so if I have my w and this is a function to the real line, and you think of this as the real line, and I'm encoding the various critical values in the real line, I basically have q critical points in w with index I, which are like those ones here below. I have q critical points in w of index I plus 1, and the critical values are shown up there above. And I'm going to have maybe some, since I am in semicolon alpha, I'm going to have some cusp critical points of index I in W, and this is shown like with this green dot here, the critical value of that cusp critical point.
I like that definition. I would just leave out the previous paragraph, just give that as the definition, because then it's just easy to understand. If you talk about separating, like then there's also topological implications, what you mean by that.
Yeah.
Because this is now like a very more clear definition.
Yeah. Well, isn't, I mean, I think they're equivalent, but you
quite a big proof, because to separate it, how do you know there's not a hole that you can get to it somewhere else? You know, like it means it's completely closed by the.
Oh, I think I use the word separated in a colloquial way rather than a precise mathematical way.
So that's why this last one is actually the definition.
Yeah, exactly. I agree. Yeah, I didn't mean it in a precise. I didn't mean it. Yeah.
Separation axioms.
No, no, I did it. Might be true, but I haven't thought. I didn't think about it as I just, you know, in my mind there's like this path of functions, and then you like on the left you have, you have something like that. And then on the right, you have two like extra things showing up, and then in the middle you have this kind of. So that's what I.
Okay. It's one of the exit points out of this region.
Yeah.
Because there's other things you could cross those critical points at the top. Those are other gates.
Right. Exactly. Yeah. So is it exactly? So is it clear what f? Yeah. What is okay. And now I want to define f sub I, where I'm going to take the union over all q greater than or equal to 0 of these spaces. So what are the functions here? They're basically Morse functions that well, let's not think about that for a second. We're basically Morse functions whose critical points only have index I and index I plus 1. And there is exactly the same number of index I and same number of index I plus 1 critical points. That's what this space consists of. I guess I'm here having q greater than or equal to 0, so I'm also including here all Morse functions without critical points as well. That's the q equals 0 case. Okay. And I'm also including, you know, like for any q, I'm including things of this form as well. That's what all the smooth functions, real life functions on f sub I look like. Is that relatively clear? And then I'm just looking inside here, and I'm putting a like superscript 0 for all those who happened to be excellent Morse. So no two critical points have the same critical value. and a subscript, I guess a superscript 1 for all those that contain a cusp or a crossing. And I'm also denoting by f tilde sub I the union of the previous two. Okay. That's a bunch of definitions.
How can it contain a crossing? Like if I comma q is only Morse functions that like.
I can have something like that.
Now I'm very confused. If
sorry, when I say crossing, sorry, that, okay, I see the confusion. I misspoke. Sorry, I just meant two critical points with the same critical value.
Oh, I see. Okay, cool.
Which is something that I'm also like, I've secretly allowed up here.
Coincidence.
Yeah, coincidence.
Okay. Yeah. Okay. You have allowed it up there.
Yeah, I have allowed it up there, and now I just separate the case when this doesn't happen and the case where it happens. Okay. But yeah, exactly. Okay, are we happy? So the theorem that we're basically going to prove today is, or at least I'll show you how to prove it, is that if you give me V, and now I'm assuming that V is compact and simply connected, and as before, it's of dimension n-1, and I'm now assuming that n is greater than or equal to 6. So I'm making all of these assumptions that show up in Cerf pseudo-isotopy theorem as presented the first time. Then under those hypotheses, if I choose any I from 2 to n-3, this subspace of the space of smooth real valued functions called Fi is path connected. And this is equivalent to the following. So let me put them one next to each other. So under the above hypothesis, so I'm keeping the hypothesis the same. If you give me any two excellent Morse functions that live in Fi, they are going to be connected via a path which lives in Fi tilde. That's the condition of here being path connected, basically. Okay, and that's what we're going to try and prove. And I guess in order to prove this theorem, what we're actually going to try and show is that if you give me any ordered Cerf path between excellent Morse functions in Fi, there's going to be a homotopic real boundary to an ordered Cerf path in Fi tilde. That's the thing that we will try to prove. We know that an ordered Cerf path will always exist. That's from the previous talk. And now we're going to take such an ordered Cerf path as an input. This ordered Cerf path, a priori might have might have critical points of whichever index, but we're going to show that we can only, it's okay to only keep critical points of index I and I plus 1. And we'll show how to kill everything else. And we have, sorry. And we also have freedom of choosing our I here. We can choose whichever I between 2 and n-3, and that's going to be true. And let me just say why this is useful to us. Basically, if this theorem holds true, what it says is that I can always find between any two Morse functions with no critical points, I can always find a Cerf path whose Cerf graphic is going to look like that. I'm going to have basically nested cusps. Here I will have all critical points of index I. Here I will have all critical points of index I plus 1, and I might have some crossings between them.
So I'm confused by that because you're starting and ending with functions with no critical points.
Yeah.
Whereas the theorem is saying that you're starting and ending in Fi.
Well, it's Fi0, and Fi0, remember, it was the comment I was making up here. When we defined Fi, we included the Q greater than or equal to 0. So we included the Q equals 0 condition. So this Q is the number of critical points of index I. So when Q is 0, we have 0 critical points of index I and 0 critical points of index I plus 1 and nothing else. So in particular, we have 0 critical points. So the space of functions with no critical points is actually included in Fi0 just by how we set it up. If I had written greater than here, then your concern would have been very valid.
So let's go down a little bit. So you're saying I can start with a function with no critical points, and then I can get to a function with no critical points. Where's the I coming from?
The birth here. Oh, the I choose.
Just travel up slightly to those.
Right. So I can choose whichever I between 2 and n minus 3. I choose that.
Okay.
Any I would work.
Okay.
And
so let me just understand the path in Fi0. These symbols are difficult to say. Like
I know.
Cryptic,
I'm
right?
sorry. Yeah.
So Fi0 means no critical points, despite the weird I. It actually
no. Sorry, the 0 stands for excellent Morse.
Including the functions with no critical points.
I don't have a notation for that. I haven't had a
but Fi0 means excellent Morse function with I critical.
So Fi0 means excellent Morse functions whose only critical points are of index I and I plus 1.
Yeah.
And there is going to be like or no critical points.
Yeah.
And
I see. So and I has to lie between 2 and n minus 3, isn't it?
For this theorem.
But then how can you get this picture? Because this picture has got no critical points.
Yes. What do you mean?
The theorem is promising that we can do stuff if we start and end with functions that have 2 critical points or 3 critical points.
No. The I does not refer to the number of critical points. The I refers to the index of the potential critical points.
Okay, so Fi0, just remind me what that means.
So Fi0 is the consists of excellent Morse functions that, if they have critical points, those are going to be of index I or index I plus 1. And there is going to be exactly the same number of the index I and the index I plus 1.
So the drawing you drew was like a special case of such a function.
Exactly. Okay. Well, no, the drawing that I'm...
This drawing, does it mean the left is with no critical point?
Yeah.
Or means the excellent.
No. So I'm just writing here basically an example of a Cerf path in that.
Just maybe label your drawing a little bit. So that thing on the left-hand side is living inside.
Yeah. So here, this whole thing here is Cerf graphic of a path in what I called above F tilde I, which was F0I union F1I. So these, on the left-hand side, I have functions f and f prime with no critical points.
They say they're elements of Fi naught.
Which are elements of Fi naught, exactly.
And they happen to be, just write the f in Fi naught. And they happen to be in that part of Fi naught which actually has no critical points.
Exactly.
Okay. Okay. Cool. Thanks.
Wait, before you continue. So we're taking the functions as not critical points, not any functions in F, not excellent Morse functions.
Well, so Fi naught consists of excellent Morse functions that either have no critical points, or if they have any critical points, those are going to be of index I or of index I plus 1. Here I'm just showing an example of. So in the theorem, we are not the theorem here, I am not supposing that we have to start and end with a function with no critical points. We can start and end with any function in Fi naught. But the way we are going to care about it in implementing it for the pseudo-isotopy theorem will be in starting and ending with functions with no critical points.
Okay. And one last question for me. In that middle thing, what can happen? Like an index I can't cross over an index I plus 1.
No, because that would be not ordered anymore.
But I can cross an I.
I can cross an I. Exactly. So all the crossings are going to be within the index I critical points and or within the index I plus 1 critical points.
Okay.
But there's not going to be anything. But like you won't have any crossing from I to I plus 1.
Okay.
Yeah. Is that okay? It's. I mean, there's so much. It's like. Because when we actually get to like the proof, it's like very visual, very nice, very appealing, very engaging. But up to there, you have to introduce so much. And the thing is that you have to introduce lots of things which, I don't know, like very similar things have been used to denote very different things in the past. So it's very that was the most difficult thing also for me to kind of like understand.
Maybe you can sort of give it a whitewash or a refresh.
I mean, at least
some of this notation.
At least for this lecture, I wanted to keep. I think for some of the previous lecture, I kind of like gave different notations, but for this one, because I also understand the list, I kept very the same notation as Cerf, but that was the only thing that I guess I Cerf denotes that Fi tilde 0, but
that's crazy.
I refused to add the 0 there. But
okay, good.
but then you know the thing that we are not going to see, and it's like beyond the scope, is then that if you have a path which looks like that, then there is an argument which I still don't understand quite. But it's an argument that uses algebraic K-theory that shows you then how to eliminate critical points in a path whose graphic looks like this. That's like a separate. That's going to be the last piece of the argument required to prove the pseudo-isotopy theorem, which we're not going to see. But what we are going to see is how to get into the reduction.
So we're going to at least reduce it to that. So we can say we can at least. We can connect F and F prime by a path that looks like that.
Exactly.
And then the rest is algebraic K-theory to simplify.
I mean, if there is interest, maybe after a month or two, once I understand it, I'm happy to do it. But
the original path we were given that went from F to F prime had all sorts of weird stuff happening in the middle. And we're going to simplify it to this as a new step.
Exactly. Yeah. So we simplified already to something that's ordered, but still something that's ordered can have all sorts of critical points and stuff. And now we are going to get this thing that's ordered and simplify it into something that's like.
For example, we are going to cancel all the critical points that aren't of index I.
And I plus 1. Exactly. And I get to choose the I. So I mean, for any I from 2 to n minus 3, I can do that. Yeah, that's what I'm promising. Well, of course, I'm promising to show you the proof strategy for doing that rather than like all the details. But yeah. And in order to prove this theorem, we will follow a strategy that's very similar to the one we used in ordering Cerf graphics. We'll do a very, very similar thing. But before we do that, we have to introduce some more stuff. So let's take a deep breath. I mean, so it's actually not that bad. It's basically these Fi zeros. I'm going to enhance them a little bit to these Fij zeros. So I'm just going to like write down like a generalization of them. So what are the Fij's? So if I have I and j from 0 to n, I denote by that this space of ordered excellent Morse functions whose critical points have index that lies in the interval I, j. So the thing that I denote by Fi0 before here would be Fi, I plus 1, 0. and I just now allow more critical points beyond those of index I plus 1 up to index j. What I just said is a little bit of a lie because like if you remember the fi is 0, I also told you that you must have exactly the same number of index I and index I plus 1 critical points, and I am relaxing this condition here. Okay, so that's the two differences between what I've defined already and what I'm defining now. And well, we relaxed this condition. Maybe we relaxed a little bit too much. So I guess I would like now to write down an analog of the fi comma q. So the I comma q were those who had exactly q critical points of index I and index I plus 1. So the analog would be if you fix a k for any k greater than or equal to 0, this is going to be my space, and that will be all those functions here in f0 I comma j that have at most k critical points of index I. So I am just controlling how many points of index I can occur here with this extra variable k. It's going to be at most k. The reason why I'm doing that is because there is a very useful filtration that I can use. So if I write, for example, fi comma j semicolon 0, that means that I have at most 0 critical points of index I, which means that I actually leave in fi plus 1 comma j 0. And I can carry on, so like with this filtration all the way to fij.
What I'm saying to you is that at the end, I might not keep up with the notation, but it might not be useful for this talk. But when you're writing this up, like it'd be nice to just have an example path that you start with, and then you just sort of show how the simplifications that can be done.
Well, we're going to do that.
You're going to do that.
Yeah.
And that's all that I care about. The notation is just frills afterwards.
I agree with you,
Yeah.
and we're going to do that. But I just don't know.
Yeah, that has to.
Like you have to. It's one of those things where you have to say the notation. You're not going to fully remember it, and then we're going to use it in practice, and then you'll come back and do. But I don't know of any way to like. Because I need to somehow introduce the theorems that we're trying to prove, and
as I go back to the way we introduce this notation,
I should actually, sorry, because here I can actually draw a picture. So maybe I can draw the same picture that Bruce you thought was useful earlier. So let me do that. I should have done that. Sorry. So, oh no, I put the page in the wrong place. Sorry. I want to put the page here. So what are these mysterious F0 ij? So what is a Morse graphic for those? It's like, so here I am excellent Morse, right? So I have, these are all, I know, index I critical points, and then I have some index I plus 1 critical points, and then I have some index j critical points. Okay, and all of these critical values here, like there is exactly one critical point in the pro-image of these critical values. That's what this 0 here denotes. And if I ask for the semicolon k, then this is at most k.
Okay, what?
Such points.
I see. Good.
That's this notation.
Yeah, but from I, with the index from I to J, right?
Just for I.
Just
So,
for I.
wait, what?
I mean with the K.
Yeah, no, I exactly. It's just for I. So this is at most K critical points of index I.
No, has nothing to do with the J.
No.
Yeah, it's weird.
So the K has nothing to do with the J. No.
Okay, no, that's what I was confused.
Yeah. It's a very non-symmetric definition.
Yeah. Okay.
And
First
that's.
I was thinking like K, but with the index from I to J.
No.
I think because we're going to attack from below.
Exactly.
So
We're also going to attack from above,
attack from
but we are at least in the beginning attack from below.
We have to monitor the defenses very clearly.
Yeah.
So we know what we're up against.
Yeah. So you say that jokingly. It does feel like a very physical proof, like when you actually, yeah. So does it come?
No, so like if K is 0, okay, it's equal to 0 means
Yeah.
not such a point, right? Yeah.
Exactly. So if K is 0, that means that that's very good. So if K is 0, then let me use another color. Sorry. That's not what I wanted to. If K equals 0, then I land in F0 I plus 1 J. And I don't have any information, like I can't tell you how many of those at most going to be because I didn't keep track of this information. But yeah, but if K equals 0, then all of that is gone, exactly. And I start with I plus 1 critical points. Okay. Are we more happy with the notation? Yeah. And basically, you basically said that already, but the whole point is we're going to use this filtration. We're going to use inductive arguments with this filtration to attack the critical points from below, and then we're going to dualize and attack from above. But that's the point. And I say we analogously define f tilde of I comma j semicolon k, where we just also include cusps and crossings. But I'm not going to spell that out in detail. I hope it sort of intuitively somehow fits in. So is that relatively clear what the various sort of new definitions are? I don't think I actually have to define any new spaces, which is good. Okay. But I do have to define a lemma. So what does the lemma say? The lemma says, if I am, you know, these are hypotheses that I now have to keep assuming all the time. So if n is big enough, namely greater than or equal to 6, and if v is simply connected, and also if I have this restrictions on I and j, so I is less than or equal to n minus 4, j is greater than or equal to I plus 2, and k is greater than or equal to 1, then every surf path here, so what are surf paths here? I start with excellent Morse functions in Fij0 with at most k minus 1 critical points, and I have a path where the indices still remain within I and j, but within the path I will have at most k critical points. So within the path I have perhaps an extra critical point of index I introduced than I did in the endpoints of the path. So if I look at paths like that, those are going to be homotopic in curly F rel boundary to paths where I'm staying within having at most k minus 1 critical points of index I. Is that?
Can you repeat this notation? The
Yeah.
soft path in this interval.
Yeah, let me.
It's not an interval, it's like a pair. It means
Exactly.
you'll explain.
I'll try and draw a picture which might help or might not help. So let's see. Let's suppose that. So what I'm going to draw. What I'm going to draw is not a Cerf graphic. What I'm going to draw is some vague picture of curly f. And I will distinguish between, let's see, this lower half is f I comma j with at most k minus 1 critical points of index I. And the top is I comma j with at most k critical points of index I. And I have some kind of path here. Okay, so I start with a point which I'm calling f. So f lives in curly f of ij semicolon k minus 1. F tilde lives in curly f of ij semicolon k minus 1. These are all, sorry, there should have been tildes here. These are all, so the f and the f tilde are excellent Morse functions. While I am writing down this path, there are going to be some times within the path where I might have codimension 1 phenomena, a crossing or a cusp occur. I'm denoting these by these pink lines. But this is something that pictorially will look like a path which starts in fij comma k minus 1, ends in fij semicolon k minus 1, but it might, part of the path might leave in fij comma k. And what the lemma says is that under the hypothesis that we're working on, like V being simply connected and of dimension and being greater than or equal to 6, any such path is going to be homotopic real boundary to a path which, let me use a different color for. Yeah, any such orange path will be homotopic real boundary to a blue path. So it's going to be a path which lives entirely within those functions that have at most k minus 1 critical points of index I. Does that help?
Do you have the explicit function for that homotopy? Or it's...
No, definitely not. Very far from. But I do have. I mean, it always depends on by what do you mean explicit? Because I mean, I wanna have something that, like I have something which I think is like as explicit as it can get in some sense. In that, like I'm showing a generating set for what such paths might look like in terms of their Cerf graphics. So the graphics of their critical values, and an explicit set of moves that you can do to reduce them to paths like the blue one. So this is what we're going to talk about quite extensively in a few minutes, maybe more than a few minutes, but that's like, it's fairly explicit in that there are like explicit pictures, but yeah, if you expect like actual equations, then definitely not. No, that's, I don't even think it's possible. Yeah, yeah. How are we doing?
Fine.
Yeah, hanging in there. Okay. That's what this lemma says. Okay, and there are some restrictions for I and j in this lemma. Okay. And I guess what I would like to show is how this lemma implies the theorem. Okay, should remind you what the theorem says. The theorem is, where's the theorem? The theorem is this theorem, that any two elements of Fi0 are connected via a path in Fi tilde. That's the theorem. I'm going to show how the lemma implies the theorem. Is it clear? Okay, first of all, some things to note about, which is that, so if you give me any path here, so this is a path which starts and ends in Fi plus 1 comma j 0, but the path itself might live in Fi comma j. Right, so here we start with like endpoints that don't have index I critical points, but throughout the path we might introduce index I critical points. Basically, I want to use the lemma to show that all of these paths can be homotoped into paths with no index I critical points. That's what I want to use the lemma to show that. And the first thing to note is that every such path must lie in Fi comma j semicolon k for some non-negative k. That's just from compactness. Like I'm going to have at most k critical points of index I introduced, if any of them are introduced, where k is some finite integer. Okay. And basically the idea is to use like it's just an inductive argument. So remember that this space is just okay. Oh no. We'll get into the pictures soon, but just a little bit more patience with me here. It's just like this F0 I plus 1 comma j. This is just Fij, where you have at most 0 critical points of index I. It's like basically the observation that you had made above. And if I have a path with endpoints here that lives in Fij comma k, then I can use the lemma inductively to basically make k smaller and smaller and smaller until it hits 0. So I can like live inside here. So that's what allows me to throw away the index. That's what allows me to use the lemma to throw away all the index I critical points that have been introduced in the path but didn't live in the endpoints of the path. How is that? This is like the last bit, which is, I think, bad, then it's going to get better.
Can you repeat what you just said?
Maybe I should repeat what we're trying to do. So, like, what I'm trying to do is I'm trying to use the lemma. So this is a lemma that we just introduced, which tells me that if I start with like functions with at most k minus 1 critical points of index I, and I have a path that might introduce an extra critical point of index I, then I can homotop this path into one with at most k minus 1 critical points of index I. I want to use that lemma for basically like to write down a very similar picture. It's just that the picture now looks like that. So this is I comma j, and this is I plus 1 comma j, which is the same thing as I comma j comma 0. Okay. So what I want to do is that if you start with a function or like two functions with critical points in the I plus 1 comma j interval, and you have a path that might introduce an index I critical point, I want to homotop this into a path that has critical points within the I plus 1 comma j interval throughout. So is what I'm trying to do clear, and is it clear what the difference is with what we are assuming, which is the lemma? That's the first thing. Is that, yeah? Okay, and basically what I'm saying is that if my path lives in Fij, this Fij must be Fij comma k for some k. I'm not telling you what the k is, it doesn't matter, but there exists some k so that at most k critical points of index I will be introduced within the path. No? Not happy?
It's just formal stuff. Don't worry. Wait till you get to the example.
Okay.
This is just formal things.
Okay.
Because I was just wondering the k that you just introduced there, because the function with the k critical points with the
Of index I.
with the index I.
Then you have infinite critical points.
No, because my manifold is compact.
Okay.
So I have like every function is going to have at most finitely many critical points. That's where compactness is the input to the story. Yeah, otherwise I'd be quite screwed because of I wouldn't be able to do what I'm trying to do. Yeah.
Is it trivial to see it?
Which equation?
The equation of the one that introduced k for some k.
Well, I'm not. Well, I mean, all this is saying is that if you give me a function with critical points that whose index lives in the interval I comma j, I know that this is a function on a compact manifold. So I know that I'm going to have at most finitely many critical points at all, like of any index. I can't have infinitely many critical points. So that means that I'm going to have at most finitely many critical points of index I. So there will exist some k such that I'm going to have at most k. That's basically what this equation is saying. And so here I have a k, here I have a 0. I'm basically in the same situation as above, but now I'll be using induction. And I'm gonna, so first I'm gonna turn this k into a k minus 1, then into a k minus 2, all the way up until it becomes 0. And that's like an inductive argument. And that just shows this bit. That just shows that if I have a path that introduces some index I critical points, I can homotop it into a path where I throw away those index I critical points that I have introduced. That's what the lemma lets us imply. Is that better? And then the idea is, you know, if you give me two functions in fi0, well, there is going to be an ordered path between them, right? That's what we saw like last time. An ordered path, I mean, I'm not making any restriction on what indices show up for the critical points. So an ordered path is going to live in f tilde sub 0, n, because that's the range of critical points I can possibly have from index 0 to index n. And then using 1, well, also 2, which I'm not going to mention. But yeah, anyway, using the above, we can get an inductive argument that kills the lower index critical points up to index I. And then also the dual argument will kill like critical points from above up to index I plus 1. So it's like, if you believe the lemma, then you should believe the theorem. That's basically what I'm trying to say here. And now I can try and tell you why you should believe the lemma, but I can also pause for questions or for a break.
Let's pause for a break.
Let's pause for a break. So it's a bit heavy. Yeah.
No, that is possible, I agree.
Okay.
Okay.
Are we ready?
Yeah.
Are we strong?
Yeah.
Okay. Dario, can you hear us?
Yep.
Okay. I wanted to write one more formal thing up there, but I'm afraid that I will be get kicked out of the room. So I'll go straight. We don't need it. I don't need to be fancy. So I'll go straight to pleasing the crowd. So but now we're starting with the pictures. Okay. I just so this is the picture that I've already like drawn previously, and that's the picture in which we are going to like start doing things. So we start with, so this is a path in a space of functions, okay, and we start with f and f prime, and both f and f prime live in what previously I was denoting f0 ij comma k minus 1. So both f and f prime are ordered excellent Morse functions whose critical points have indices in the interval I comma j, and there is at most k minus 1 critical points of index I. That's what f and f prime are. This is a path of those in the space of in this like space f tilde. And you know, when we cross this pink line, it means that we've introduced an extra critical point of index I. This is the going from k minus 1, at most k minus 1 critical points of index I, to at most k critical points of index I. That's this pink crossing. And then these blue crossings is some codimension 1 phenomenon, like a cusp or like having two critical points with the same critical value. That's what this picture is. And our goal is to take this path and homotope it into a path that lives only in the bottom half. Okay, that's the goal. And so this, first of all, this resembles very much the situation that we were at last week. Like I basically had drawn the same picture, and we were like doing sort of like very similar stuff. So and the first thing, if you remember what we were doing last week, is I tried to define some paths that, like, from each point in those intervals, like go down like that. That's what we were trying to do, so that we simplify what things we have to work with. Basically, I want to reduce this general case to a bunch of cases where I only have at most one blue line in here, at most one codimension 1 critical like phenomenon occurring. And so these paths, which take me from a point here to a point here, these green paths, these are what I've called in the beginning Smale paths. Okay, so that's like first thing that we see is like Smale paths are paths which have a graphic like this. So what does that graphic do? So we start with a function, and the function that we start with, let me say, there could be other critical points above. But the function that we start with has, say, I plus 1, I plus 2 critical points. And what I'm doing in a Smale path is I introduce a birth. There is a birth between the I plus 1 and I plus 2 level. So this birth gives rise to an index I plus 1 and an index I plus 2 critical point. Then the index I plus 1 critical point crosses all of the other index I plus 1 critical points. It comes down and it kills the top index I critical point. Okay, so that's what small paths do. These are just like one parameter paths. We haven't really killed anything with them, but we've interchanged an index I critical point with an index I plus 2 critical point. That's what those paths do. Okay, and that's exactly, that's exactly what we need in order to go from something here to something here. So these green lines are small paths. So when we are here, it means that we have an extra index I critical point, and we want to go to something that doesn't have this extra index I critical point. So we are going to interchange it with an index I plus 2 critical point. Sorry, we interchange it. Yeah, we interchange with an index I plus 2 critical point. That's what the small paths do. And under the above hypothesis, I'm not going to go through the proof, but under the above hypothesis, small paths always exist. So I can always find those green lines. And as a result, there is 3 cases that I have to worry about in order to kill stuff. It's this case where here I have an inverse small path, here I have a birth-death recrossing, and here I have a small path. So this corresponds to something like this. You don't see?
Go back. Where's the path when you say a small path? Okay, fine. Just drawing green the path that is a small path is like.
Guess I'm not very sure how. I think I don't know. I was thinking of something like that, and then something like that.
Okay, happy with that.
Yeah.
Yeah.
And then the other case is I might have a birth and then a small path. It's what I would be getting here. And then the last case is I might have an inverse small path and a death, which is what I would be getting here. Yeah.
Yeah, so exactly the existence of that Snell path, quite a lot's going on there, but we'll come back to that because I mean there you are introducing critical points and killing them. So
yeah,
you are doing some stuff there.
I'm doing stuff there, yeah.
But let's see you tackle these cases first. Yeah.
Yeah.
But I didn't see, why do we still have the that is why do we still have crossing? The ball on there.
I'm just saying I might. I'm not saying that I must.
Yeah, but
because in general, like a general path is just going to look like that.
Yeah.
And these blue things are either cusps or crossings, like have critical points with the same critical value.
Yeah, then you have the small curve, which is.
Yeah. So here, I basically what's happening is I am at this point. Here I went down, and then I went up again with the inverse, and then I went down and went up again, and I'm just basically looking at like something like this.
Oh, okay.
And so this something like that. Oops, something like that is what corresponds to.
That's why we have inverse. Also.
Inverse, exactly. That's where we have inverse small path.
I was looking on the first row.
yeah,
Okay.
Exactly. Okay. And now we basically have to translate what each of these pictures might look like in terms of Cerf graphics, and then operate on those Cerf graphics. So the first kind of lemma is that there are 5 types of Cerf graphics that we have to deal with. And it's those 5 types that I am showing you here. So let's go through them and see like how they appear.
Corresponds to which of the cases there?
That's what I'm going to just say now. So so this case here is an inverse Snell graphic with a Snell graphic.
But that's one in one of your cases, but that's
So implicitly it is, because basically and you'll see that in a second, but
it's not the inverse. It's not the inverse of the Snell graphic. It's a separate one. So
so it's basically a case where, you know, I don't have anything here.
Yeah.
Which you're right. Technically, I didn't include this as a case, but what we're going to see in practice is that, okay, I might have something here. I might have a birth, death, or crossing.
Yeah.
Which might be completely disjoint from everything else that's happening. So I can just like push it away and be left with just an inverse Snell path composed of the Snell path.
Yeah.
So in practice, for lots of these cases, that's the only thing that I have to worry about.
Yeah, but you certainly do need to worry about that.
Oh, you certainly do need to worry about that, no doubt, exactly. Okay, so here, what do I have? Here I have an inverse Snell path, a crossing, and a Snell path.
Yeah.
Okay, so this is one of those cases of this form.
Yeah.
And here is another way in which I can have an inverse Snell path, a crossing, and a Snell path.
I mean, you already tabulated them all for us already. That's nothing new here.
There's nothing new, but I have to tell you how these are the only things that I have to consider given what I tabulated above.
Okay.
Right. So these 3 cases, so type 1, type 2, and type 3, basically cover the inverse Snell path, crossing, Snell path.
Yeah.
This case is when the crossing happens disjointly. So you know, I might have a crossing up here, and I can just I just push it away.
Yeah.
And only have to worry with that. Or I might have a crossing down here. I can just push it away and only worry about that. If I have a crossing here, that's this case. And then the only other case is if I have a crossing between the top I and sorry, that would be, I guess, the top 2 index I critical points. That's this one. So these are all of the inverse Snell, crossing Snell. Then I might have inverse Snell, cusp Snell. Okay. And that's really the only thing that I have to worry about, and everything else I can just push away from the diagram and be left with something of this form. And then this last one is I have a birth and then Snell. So this last one corresponds to this case.
Yeah, I agree. But the statement it says there a lemma, but like basically this is just a tabulation. It's clear that there's nothing else that can happen. I mean,
well, it does require proof. No,
I mean, it's like saying lemma. There are 5 things in this picture. Count them: 1, 2, 3, 4, 5. Like what's the?
No, I think I disagree, because I think there is still. I don't disagree that it's not a difficult lemma to prove, but I think that there is something.
What does need to be proved? Just that if the crossing occurred at the top or at the bottom, then it's irrelevant.
Yeah,
but that's clear, right? And then,
yeah, exactly.
Okay.
Yeah, you basically have to show exactly that if the crossing or if the cusp doesn't appear where I show it to you to appear, then it's irrelevant.
Okay.
I'm not saying that's difficult, but I think. I don't know. Yeah, okay. I wouldn't mind it being called lemma. Yeah, okay. It's not deep. Like this is the only thing that we've done so far that's actually deep, which I haven't proven, is that under these hypotheses, Snell paths always exists. Like that's that's the difficult thing that I'm pushing under the rug. Everything else is like is fairly clear, And the plan now is to basically just deal with each of these types separately, and like kill critical point, like kill the top index critical point in each of them. That's what we are going to try and do. And I'm not going to do it. Well, I'll do it for each of these types, and some of them are like very easy, some of them are a little bit more difficult, but all of them have quite nice pictures that are worth going over. The first thing, this is going to happen in 2 stages. The first stage is getting to a point where I have a swallowtail appearing, and then in the end, I'm going to do that for all of them, and then in the end, I'll just tell you why we can like cancel the swallowtail. So it's going to happen in those 2 stages. Okay. So let's get something of the first type. So the first type looks like that, and I'll just get you through like the surf moves here. The first is this like independence of critical points. So
is that English or French?
That's French. I just wanted to. I'm quoting directly from Surf's book here, like all the pictures and everything, and it's a brilliantly written book. It's quite difficult to.
Just because it is.
No. Beating French just makes it a little bit harder. If the maths wasn't hard already, just keeps you in the Okay, so I just want to explain how we can get from like
By the way, I was trying to, fluent French.
Oh, really?
Yes.
Oh, amazing! I wish I could say the same thing for me. It would have saved me so much. Yeah.
I would have thought you were reading French like fluently because you are using the French book.
No, I definitely not fluently. I think I've grown to sort of like understand math French without much Google Translate now, but definitely at the beginning it was all Google Translate and trying to, I know. Just, well. But that's the only place where you can learn the stuff from. Like that and John Morgan's lecture notes. But John Morgan doesn't cover everything. So he covers a lot, and it's very, 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 very useful. But really, if you want to, you gotta go back to the original. There's no other source. It's very beautifully written. But okay, so we start with something like that. Okay. To go from here to here, we just use independence of this coincidence stuff that I was telling you, and we just like push this CASP below. Now we're going to perform a big move. We're going to like take this and push it over. So that's going from 2 to 3. Important disclaimer that I have to make. For all the surf moves that I am describing, there are abstractions to be made. But the restrictions that we've done, like the hypothesis that we are working under, like V being simply connected and N being greater than or equal to 6, those imply, with quite some work, that all of these abstractions can be dealt with. I'll do that, and I'll show you maybe like a lemma that Surf proves about the swallowtail later on. But in lots of the stuff that we are doing, we are using the hypotheses that we are working on. Okay. So here's a big, and now to go from 3 to 4, all we are doing is just push this CASP on the left. Again, we are using this coincidence stuff we're talking about for these 2 CASPs. Okay, we're here. And now to go from 4 to 5, I don't know if you can see already, but it's basically, that's a Reidemeister 3 move. It's like taking this fold and pushing it over this crossing. So we are at this Reidemeister 3. And then once we are here, we basically, again, we just like use coincidence to like push the cusp a little bit on the left and right here, and we end up with something that looked like a swallowtail.
What's the difference in those pictures? I'm just trying to
Sorry?
I'm just trying to see what move was made there.
5 and 6.
Yeah.
There wasn't any kind of intricate move. I think it's just an isotopy.
Okay.
We didn't like.
You wanted to reduce the standard.
Just want. I don't know. I just want.
Yeah.
Okay. Yeah.
Okay. Good.
Nothing really goes on from 5 to 6.
This I can believe. I can believe this. Yeah.
Yeah.
This I'm happy with.
So it's like,
Yeah.
if you start from here, you believe that we can
Yes.
end in here.
Yes.
Perfect. Okay. That's the type 1.
Because I don't think there's any series of structures to beat, for example. Like you can always do it. Yeah.
Well,
And
the most serious abstractions are for the swallowtail,
Yeah.
but there is definitely, I mean, there's definitely something to be
and
said.
We haven't cancelled any critical points.
Huh?
We haven't cancelled any critical points either. That's where I know. But it's fine. I'm just saying. So
Well,
there's
but you see now, I mean, but you see how we're going to cancel them. I mean,
Yes,
basically
now we're gonna do it.
now this is.
that's
So I think I've delivered already something
You
like
delivered
yeah. I just want to do that for all of them, and then deal with the swallowtail in the end.
Good.
But and again, I don't know if I'll deal with it in a very satisfactory way, but at least I'll say something. Then okay, what's the second type? The second type is this. So the second type reduces to the first type. Can you see how? Or should I should say, it's like you're taking this crossing and you are using a Reidemeister 3 move to like push it away. It's like okay, I'll introduce a page. Let's see if I can draw here. My drawings are going to be very bad. Maybe okay. And you have okay, I'm sorry. This is what the second type looks like. And well, what I'm saying is take this crossing, push it, well, to the left, to the right, it doesn't matter, wherever you want. So I'll make it okay. I haven't done anything yet. I just pushed it to the left a little bit. And now when I'm here, take this and push it over, like do a Reidemeister 3. So then I will have like something like that. And that's the same thing as a type 1 thing that we've seen. Yeah. So that's how we go from a type 2 to a type 1. Yeah. Type 3 is the hardest, so I'm going to leave that for the end. I'll go to type 4. type 4 is this is the type 4, and I'm doing basically two bigs. So the first thing that I'm doing is I'm doing a big where I'm pushing this CASP over here, and I end up with a picture like this one below. Can you see it?
Yeah.
And now the second big is going to take this CASP and push it away.
Oh.
And then I will be left with a type 1 thing again.
Even that I'm happy with. I know there's no obstructions to those. I only know this because of your work right now.
Well,
but anyway, yeah.
No, I mean there are abstractions to everything that I'm saying. I'm just trying, but you know, my goal here is to show the structure of the argument, and I just want to show pictures that are at least believable, and then we can go back to them. Type 5 I think is the easiest, reduces to first type via independence of singularity. So let me go back to type 5. Type 5, can you see that already? Or it's basically, if you push this CASP to the left, here down, you're going to end up with a swallowtail. Is that, yeah?
Yeah.
And type 3 is the hardest, so we can deal with type 3. There's lots of stuff going on in type 3. So first of all, type 3, we're not going to directly be able to deal with it, but we are going to be able to deal with it upon introducing an extra Smale path. So this here on the right is what I've shown above as a type 3. So in order to simplify a type 3 thing, I'm going to introduce a Smale path. Of course, I can't do that, but I can always introduce a Smale path and then it's inverse. I'm just not showing its inverse here, but it exists, okay? And we are going to worry about now this picture. So the first thing that we do is this merge on merge move. We have those two CASPs here, and we merge them together. It's this move. So it's like this fold line is this fold line, and then the united CASPs looks like that. Okay.
But there I'm a little bit more worried, because that does seem like something that can have some serious obstructions.
So there I'm also a little bit worried. It's so this is the so-called independence of births and deaths. So the way you deal with that is you look at the middle Morse function, and you have to argue that if you introduce a birth here, there is like a homotopically unique way of doing that. And so what Smale proved is that that's always going to be the case. So if you have a level set which is connected, then if you want to start a birth at that level set, you can do that in a unique way up to homotopy, which is quite believable.
Okay.
So
in amongst those would be the one which would be like the inverse of this one. So
exactly. Okay. Exactly. That's the point. And you know, we are working with V being simply connected, in particular connected. Of course, the actual manifold in which things take place is W cross I. So what we want to be connected, is this level set here. And in particular, what we want is that if you give me something that's simply connected, like V, and I do index I surgery on it, I end up with something that's connected, which I think that's definitely true, but I think that the index 0 and index 1 surgery, I mean, index 0 surgery is just, you're just literally adding a disjoint union. So you end up with something that's disconnected.
Yes.
And I don't think, I haven't seen in this particular case a separate argument from Cerf, so I don't know if there is something I don't understand very well.
Okay.
But for the vast majority of cases,
Yeah.
the abstraction to doing this move just is follows directly from the fact that these connect. Yeah.
Okay.
And that follows because we start with some V which is connected, and then we do eye surgery on it, and so we will end up with connected things all throughout.
Okay.
So this is where, so I haven't,
Yeah.
when I is 0, 1, I have a little bit of a fear. I spent all of yesterday on it, but I haven't. Yeah, that was the. But at least for all the other cases.
I mean, weren't we specifically excluding those cases already?
Yeah, not yet.
Exactly? Okay,
Not yet.
Okay.
We've excluded them in the previous formal stuff where we used this as an input, but but no, I mean we have to like I have to kill the index 0 critical point. Someone has to do it. So they might exist and they have to be killed for sure. All we've done before is that I know that I can end up in something that has index greater than or equal to 2 and less than or equal to n minus 3. But that's not where I start from.
Okay. Good.
So there I have maybe a small question mark, but that's the kind of abstraction that you have to worry about in this case.
Yeah.
Okay. And then the rest is basically bigs and Reidemeister 3s, but so going from 2 to 3, we basically do two things. The thing that we do is a big move here. So we take this cusp and push it to the left of this curve. Okay. And the other thing that we do is like much less dramatic, is we take this cusp and we use this coincidence thing to like to just like move it to the right over this crossing. So that's from 2 to 3. Happy? And from 3 to 4, is a Reidemeister 3. So I don't know if you can see, we have the crossing here. Oh gosh, I'm not tall enough. We have a crossing here, and we have this like, and then we push it to the right. That's what going from 3 to 4 buys you. And I believe what else? What's 4 to 5? 4 to 5. 4 to 5. Sorry.
I mean, 3 to 4. You're not even doing a Reidemeister 3. You're just dragging it a bit.
No,
What is the dotted line?
The dotted line, I think, I think it was there to try and help you. My understanding is that it was there to try and help you see what happened.
I see. It is a Reidemeister 3.
It is a Reidemeister 3, right? Because here we had this, and now we went to the other side. I'm sorry, give me a second. I believe the 4 to 5 is a big move here. We take this cusp and put it inside this fold.
3 to 4 is like 2 Reidemeister 3s. First of all, to get to the dotted line, and then to get to the final line.
Yeah, okay. I think that's what's. Yeah, that's right. That's right. There's 2 Reidemeister 3s exactly. And I think here that's a big. It's like you take this cusp and you move it inside. Is that true, or am I missing something?
But that R plus one thing, you're moving it inside, as you say. That R plus one corner, you're moving it
this
inside.
one. Yeah, yeah. And I think that's
a P.
Yeah. And then I think that's all that's happening.
Yeah. You're moving that R plus one P inside.
Yeah. I think that's all that's happening. And then you end up with this picture. I mean, those two pictures are the same. This one is just, I don't know, just looks more like a bird, but but here we created the swallowtail that we're going to kill.
Yeah.
So that's the
Okay.
that's the hardest one.
Okay.
Third type. Okay.
How's your power looking?
Yeah, yeah.
Okay.
Well, I don't know, but I think I'm optimistic.
Okay.
Dealing with swallowtail, I'm just gonna tell you. Yeah, I'm just gonna tell you what the theorem is that Cerf proved a long time ago and used, just to give you an idea of the sort of complexity that's going on. It's like so this is what a swallowtail path looks like, and the swallowtail lemma is that if you have f, so f is a function here basically, which is excellent Morse, and c is a critical point of index I. So here I have something of index I, that's my c, sorry, index I plus 1, and that's of index I. So I have V0 and V1. So V0 is the level set above the critical point of index I plus 1, and V1 is the level set below it. So if n is greater than or equal to 6, and my I is in this range from 0 to n minus 4, and also V1 is simply connected, or I is n minus 3, so just outside of this range, and V0 is simply connected, then if one of those conditions is being met, I can cancel my swallowtail. That's one of the theorems that Cerf had to prove. And essentially, what we have done is that we've reduced all cases to a case like this one, where we have, I guess here there's like index I things, but there's nothing of lower index than index I, and basically we want to cancel those swallowtails. In order to cancel those swallowtails from the theorem that I just told you, oops, sorry. Why can I not write in here? Wait, what's happening? Sorry. Yeah. This is my V1. I need to argue that this V1 is simply connected. That's what I need to show in order to be able to cancel the swallowtails. And if you are in high dimensions, so well, what I know is that the level set that I start with, that's like my V, I know that this one is simply connected. Okay, that's what I know. That doesn't tell me immediately that the level set that I care about is simply connected. But are you trying to capture the assassination of the critical points in real time? And so that is what requires an extra argument. And basically the argument is that if you are in high dimensions and you do like eye surgery, that's not eye surgery, that's not what I meant. I meant like index eye surgery. Then if you were simply connected, you will remain simply connected. If I is in a certain range, if I is from 2 to like n minus 3. The thing that you have to worry about is the I equals 0 and the I equals 1 case, where this is no longer going to be true. I mean, the I equals 0 case, you're adding a new extra component. So that we're going to deal with separately. But maybe I can give you a kind of like argument that you can believe in, like not a proof of what I just said. It's like, so if you haven't seen surgery, this is not going to say much to you, so you can maybe ignore what I'm going to say. But if you have seen surgery, it's like if you give me a manifold V and say, well, maybe I should say M, and say that you want to do like index 2 surgery in it. Index 2 surgery is like, it's going to be I think I want my manifold to be n minus 1 dimensional. So this is n minus 2. You know, I bed this frame sphere and then I do surgery along this frame sphere. If I look at, if this is my bedding, if I look at where S1 is being sent under this embedding, that's going to represent a class in the fundamental group. And index 2 surgery is going to basically produce a manifold that kills this class. And that's the only way you can have like your surgery impacting the fundamental group, is if you have an index 2 surgery like that. Higher index surgeries are not going to touch the fundamental group. And you know, so if you start with something that's that has a non-trivial loop, you can end up with something that's simply connected by an index 2 surgery. And then you can go the other way around. You can start with something that's simply connected and end up with something that has non-trivial fundamental group, but you will need to dual surgery to do that. So that would be n minus 2. And we are excluding n minus 2 surgeries from. So the only thing that could screw us up beyond 0 and 1 would be an n minus 2 surgery, which we have excluded. Yeah, if this said nothing to you, I'm sorry, but that's sort of something to make it believable. And then the way we will deal with the 0 and the 1 case is again, so if I is like 0 or 1, then what we're going to do is that we are going to introduce a small path again, and then we are going to bring the small path to the other side by a series of peaks and Reidemeister 3 moves to get to a picture like that. And now, directly below this, we have like one less layer of index I critical points. So I can do that for all of the layers, and then in the end I'm going to be left out with V, which is the manifold that I began with, which I know is simply connected. And then I'll kill the swallowtail, and I'm post-composing with the inverse small paths here. So that's how this is like treated separately. Yeah, and that basically concludes the end, the proof of the lemma. I can pause for questions, or
why don't you go back to the very first slide where you stated the pseudo-isotopic theorem, just that we can.
Yeah. That's how it started. Do you want the pseudo-isotopy problem, or what do you want? I don't know.
The theorem, at least. Because now we've essentially proved a certain theorem, right?
Well,
I mean, yeah.
we've reduced to the proof to something, but
Yeah, we
well,
the structure.
but that's the theorem. Yeah.
And
So this M is V, is today's V.
So we had this theorem, and then we reduced this theorem to a statement in Morse theory, which was also in that first lecture, right?
Indeed. I think I drew a better picture of it in the second lecture. Yeah. Exactly. So this epsilon of M is the space of smooth real value functions on M with no critical points. This is a path in f of M, and I'm basically reducing to like the problem that I wrote here.
Okay. So I'll want to very much thank you, Filippos, for your tremendous effort that you made giving this wonderful series of lectures. We really, really appreciate it. Yeah.
Thank you.